Right, on to the next theorem. So we're going to be talking about the mutual independence complement invariance theorem. That was a mouthful. So what is the claim? Well, it is in essence an extension of the previous theorem that we talked about. That was the independence of the complement theorem. Now, the claim, let C be equal to the set B1 through BK. And let it be a class of independent events or mutually independent rather. If we substitute for any subset thereof, the set of the corresponding complement we shall get a class of independent events and the important bit is that they are or will be mutually independent even after we substitute any number of random events for their complements. Well, that's rather interesting. Well, how do we prove this? Well, by induction, but setting up the induction isn't that trivial. It is not hard, but it is not trivial. We shall do induction. So by induction on M for, or rather where, A1 up to AN and B1 all the way to BM make a subset of C. So we take, so essentially here n plus m is equal to k. Now, why does it matter? Well, because maybe it would be easier to show by explicitly saying what we want to prove. So we wish to show that the probability of the intersection ranging through 1 to n of a's intersected with the intersection ranging through 1 to m of b complements bm's is equal to the product ranging through 1 to n of ai's times the product ranging through 1 to m of bi's complement. Now, essentially we need to verify two claims. One, we need to show that they are mutually independent, meaning we make an arbitrary choice for k or m plus 1. And then within this arbitrary choice, we'll make an arbitrary choice of k, the total sum of the split of a's and b's. And then within this selection, we make a new selection, and that will be a new choice rather, and that will be for m. How many of these k elements we will substitute for, right? And we will prove the claim only with the free choice of both, arbitrary choice of both. Now, n will be fixed and m will be variable. We will leave the induction on m. So the base case is trivial. So trivially by the previous theorem. That is to say, the independence of the complement theorem. Independence of the complement theorem. Now, induction hypothesis. Well, rather, the induction step. It is clear what the induction hypothesis is. We assume that the claim holds for m b's, and we want to show that it will hold for m plus 1. Like this. Or rather, for k and k plus 1 then. So, induction step. So, assuming the claim holds for b1 up to bk, we wish to show it also holds for b1 up to bk plus 1. Very well. The proof henceforth is nothing clever. The most interesting bit is past us. By definition, we want to show, or we will begin with the expression p of the intersection ranging through 1 to n of ai intersected with the intersection ranging through 1 to k plus 1 of bi's complement. And we will want to show that this is equal to the product of the individual probabilities of all the a's and all the bic's. So we shall use, using sigma additivity of probability and using the following formula that a intersected with b is equal to a minus, or a without, a intersected with b complement, where a is equal to the intersection. So the intersection of all the a's and all but one b. Why are we doing this? Why are we splitting it like this? Well, because the induction claim holds on this, well, the induction hypothesis holds on this set, on this A, because now we will range it only until k of BIC, and B will be equal to BK plus 1C complement. So using these two things, we arrive at the following expression. So this is equal to P of A1 intersected with A2. I will write it out rather. All the way until AN intersected with BIC intersected with BI2C, all the way until we arrive at BM. And complement. This is A minus, here we're using the sigma additivity, P of, and now A, which is the same as above, but intersected with bk plus 1, oh, here it's supposed to be k, not m, sorry, intersected with bk plus 1 complement, so simply bk plus 1. Alright, well, this is interesting, because using the induction hypothesis, the first one we can simply write out. That's the case for m equal to k, or yeah, for m equal to k. So we have p of a1 times p of a2 times dot 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 on the way, all the way until we arrive at pb1 complement times dot 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 times pbk complement minus same thing, so pa intersected with dot 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 until we arrive at b1c sorry times pa2 times dot 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 times b the probability of pb1c times dot 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 times p of bk complement times p of bk plus 1. Alright, now we can factor out A, essentially, as we defined it. So PA1 times PA2 times dot 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 PB1 complement times dot 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 PBKC. So this was common here, times 1 minus, and P, and this is why we do it, PK plus 1. Well, this is nothing more than P of BK plus 1 complement, which is precisely what we wanted. This is the product that we desired. So this concludes the proof this concludes the induction step, and thus the proof.